Hello and welcome to my talk. My name is Thomas Kuhn. I'm heading the Embedded Systems Division at Fraunhofer Jese, and today I would like to introduce our Industry 4.0 virtual automation bus concept. So in Industry 4.0, we want to enable an end-to-end communication, and the realization of this end-to-end communication is quite a challenge. If we look at the systems today, we see that PLC controllers communicate with each other using field bus protocols. We have SCADA systems that communicate with PLC controllers. We have MES systems that communicate with SCADA and with ERP. And we have ERP systems that mostly provide data and communicate with the MES systems. This yields a layered architecture that is shown here in this automation pyramid. And the reason for this layered architecture is that everybody is using different protocols and data models. ERP systems, they usually provide an interface, for example, with HTTP REST web services. MES systems do the same, but they have connectors to the field. PLC controllers, some of them are able to do HTTP REST, others you choose OPC UA. Older machines have their own proprietary variants. And in addition, there are lots of specialized protocols. So for example, in our demo setup, we have a reflective memory system, which enables latencies in the magnitude of 5 microseconds, which is much faster than Ethernet networks for small amounts of data, of course. So our challenge is everybody is using different protocols. We have this layering, and we don't have this layering because we want it, but we have this layering because we need it. And therefore, it's very hard if an ERP system wants to use data from a sensor that is in the field level. It simply cannot access this data. So why should somebody wants to do that? Well, let's have a look on a simple example. What I've shown here is a dashboard that we did create for a demo factory that provides some data to the ERP system that also uses some data from the ERP system. And what are we doing if we create such a system today? Well, we take edge devices, we attach these edge devices to the field level or to the PLC level, and then we use different network protocols, for example, TCP/IP, to get this data and to collect it into one application. But that cannot be the solution because we cannot use new edge devices for every application, and we also need to integrate the existing applications, existing databases into one common communication system. And that becomes especially evident when we look on a larger scale. So production today is no longer limited to an individual factory or to a production line, but it is a networked system of suppliers, of companies. Maybe a single company has several production plants that can take over for each other. And today, this complex system, this ecosystem, is managed manually. And here on this slide, I have shown some examples of an autonomous negotiation between companies or between divisions of a company that could happen in the future. So for example, if one device fails, like here shown, device 23 fails, another company could take over and could say, okay, I can take this order and I can make sure that the parts are shipped to you in time. Or maybe the companies could implement a load balancing, a marketplace that says, who can supply 8,000 molds? I need them in 2 weeks. please make offers. And somebody could say, okay, I have the capacity of doing that. Yeah, with my production technology, it will cost that specific amount of money. And this will work regardless on whether we are speaking of one individual company or whether we speak about a network of companies. The challenge is today we have a vast amount of communication protocols, and there is standardization ongoing. So for example, OPCUA is one big thing that will be certainly one standard in industry for automation. But we have so many protocols, not only because we have different manufacturers of communication technology, we have these protocols also because they have specific properties. High-speed cameras, for example, can create 1,000 pictures per second. It will be difficult to communicate this kind of data and low-frequency sensor data with the single protocol. And in addition, we have different protocols between the IT level and the OT level, the operational technology. And for the IoT, the Internet of Things, or Industrial Internet of Things, we again have different kinds of protocol. Here, for example, MQTT is very strong. And even with standardization in one area, we will still have the challenge to retrofit. So our solution is not a single protocol, but a unified communication architecture that defines communication primitives, a very simple type system, identifiers with a hierarchical namespace, and a flexible mapping of this unified communication architecture to technologies so that we can bridge, for example, OPCUA, HTTP REST, and proprietary field bus networks. The users in the end, they should not need to care whether a specific machine is connected to a specific network. As long as it is connected to this unified communication architecture, the gateways in this architecture will make sure that a requested message arrives at its destination. So the virtual automation bus is, on one hand, a concept that bridges communication technology, and on the other hand, a one-time interface that can be mapped to, for example, CAN bus, to HTTP REST, to other technologies, that is based on a very simple object model and on 5 primitives that gives everybody the possibility to speak with any device that is connected to this object space without having to speak the native language of this device. It connects the IT and OT levels and turns the automation pyramid, as shown, into a peer-to-peer infrastructure. It is extensible with new protocols, and I hope that I was able to generate a sufficient amount of attention so that you will be reading our paper on it. Thanks a lot and have a nice day.